Okay, let us continue. And did you think about this problem with momentum? Like, so any suggestions on how to improve without looking at the lecture notes? Yeah.
Adjust gamma.
Adjust your gamma.
Reduce gamma.
Okay, so then now we are back to the learning rate business, right? Like, so if I have to tune my gamma carefully, like it's a difficult process. Like, so like, how do I know when to like reduce my gamma or when to increase my gamma, right? So it's a bit difficult. Yeah.
If the next point is higher up than the previous point, then we decide to go back. So I can
decide to go back.
In this example, like we jumped from a higher point.
Okay. One of the issues with deciding to go back is like if you're using SGD, there is a lot of variance. So now you don't know if that was high because of the variance or because of the momentum, right? Now, let us say that instead of a ball, there is actually a human running down the hill. Okay. Now you're running down the hill, but this time not blindfolded. Okay. So normally, like you will start accelerating, like when you're going down. But when you see that there is going to be another uphill, given that you have looked ahead, that there is an uphill coming up, you will start decelerating, right? Like so, you will start decelerating even from here, like so. So from here, like you know that there is an uphill coming. So probably I should slow down my speed, right? Like so. Now, if there is any way, like you can like look ahead, then maybe you can avoid this issue, right? Like so, what we are looking for is actually a smarter ball, which can sense like what is in the front. Okay. Now, here is an approximate way to do that. Okay. So we know that. Let's go back to the equation. I don't know where the equation is. So whenever we are making updates, right? Even before computing the gradient with respect to the current mini batch, I know for sure that I'm going to add this to my parameter, right? So this part has to be computed from the data. However, this part has been already computed in the past, right? So if I have to expand my update rule, this is theta is equal to theta minus gamma times Vt minus 1 minus eta times it, right? Now we know that I can already make this update even without computing this part of the update, right? So in some sense, it gives me an idea of how I'm going to be in the future. So instead of computing this gradient with respect to my current parameters, I can actually compute this gradient with respect to my future parameters. Okay, so how do I do that? So here is an algorithm like so. We're going to do Vt is equal to gamma times Vt minus 1 plus eta times the gradient. Okay, now the gradient, instead of being the parameter theta, the gradient is going to be computed with respect to theta minus gamma times Vt minus 1. Is that clear? Okay, I think I confused by using similar V and gamma. So let's just call this as V. Okay. Then I do theta is equal to theta minus Vt. Is that clear? Now, one way to understand what is happening here is, let's say this is where I'm currently in, and my gradient says I should go this way. Okay, and my momentum is saying that I should go this way. Okay. So when I do SGD with momentum, it is going to consider both these direction into account. So on an average, effectively, I will go this way. Okay. Now, this new type of momentum that I described, right? So it is going to work in a slightly different way. So now it is going to start from here. Instead of computing the gradient at this point, first it is going to take a momentum step. Okay. Now from the momentum step, I compute the gradient. So this is, we're going to call this as look ahead gradient step. Okay. So this is a different gradient than the original gradient that we will compute on the left hand side. So my actual step now is going to be a combination of these two vectors. So this is my actual step. Is that clear? So this is a bit smarter than the vanilla momentum, like, because now, for example, like when I compute, okay, I have to go back to the diagram. So when I compute my look ahead gradient, it might tell me, oh, there's going to be an increase here. Like if you go a little bit further, so probably you should reduce your scale. Is that clear? So now this idea like of like look ahead gradient with momentum, right? Like so this was by Nestro, okay, so who is one of the famous optimization expert who has done a lot of contributions in optimization. So this is called Nestro's accelerated gradient method, okay, or also known as NAG. So NAG has even better acceleration, like and also like some smarter improvements over SGD with momentum. Is that clear? So any question about this whole idea of using a momentum? Okay, so now we can actually get back to the final issue that we discussed, right? Like, so what if my data has like sparsity, in which case different parameters have different types of gradients, like some get dense gradients, some get sparse gradients, and so on, right? Like so how do I solve this issue? Like, so did you guys think about it? Like any potential solutions? Okay, now instead of having a same learning rate for all the parameters, what if I can change my learning rate? So what if I can have a bigger learning rate for small gradients and larger learning rate for, sorry, smaller learning rate for large gradients, right? So then on an average, like I might learn more equally, right? So we're going to see a family of algorithms, okay, which is going to dynamically adapt the learning rate of each parameter individually. Okay, if you have 100 parameters, then it is equivalent to having 100 learning rates, not just one learning rate. Okay, now how do we do that? So we have a family of algorithms which we're going to call as adaptive gradient methods. Okay, these methods adapt the learning rate to perform large updates for infrequent and small updates for frequent parameters. Okay, now the simplest type of adaptive gradient method is called AdaGrad. In fact, this was one of the first adaptive gradient method, like probably in 2010, I guess, or around the time, which introduced this new trend of like coming up with adaptive gradient methods, like so, which really was one of the many reasons for the success of deep learning and deep neural networks. Okay, so with adaptive gradient methods, we were just able to adapt and optimize any complex structures, like so, which was not possible with vanilla SGD with momentum. Okay. Now let's look at undergrad first. So undergrad is really simple. Like so, like what we are going to do now. Well, let's set some notation first. Like so, we are going to call GTI to be the gradient, okay, of the ith parameter at time step t. So it's theta t comma I. Okay. So this is basically the gradient of the objective function. Okay, with respect to parameter theta I, okay, ith parameter at time step t. Is that clear? Now, if once I have this notation, now I can rewrite my regular SGD. My SGD is basically theta t plus 1 comma I is equal to theta ti minus eta times g t. Right? This is my regular SGD. Now, here is how undergrad is going to look like. Okay, so theta t plus 1 I is equal to theta ti minus, so far this is like SGD. Okay, now I'm going to divide this learning rate by some term, okay, which is basically square root of summation p is equal to 1 to t gpi square plus epsilon. Okay, so what am I doing here? So I'm dividing the learning rate for this particular ith parameter by square root of sum of squares of the gradient. Okay, now I do a squares and then square root. So on an average, this is the root mean square of the gradient. Now, in the beginning, my gradient could be 0, right? Or sometimes my gradient sum could be 0, right? And so to avoid numerical instabilities, we are going to have this small epsilon, which is typically something like 1 e power minus 6 or 1 e power minus 8. Okay, we have a small epsilon to make sure that the square root doesn't like have any numerical issues, and also when you're dividing by like almost 0 number, there might be issues. So to avoid those things, we have this epsilon. Okay, now intuitively, how would this scale the learning rate, right? So imagine I have a parameter I which gets lots of gradients. So then as it gets lots of gradients, this term is going to get bigger and bigger, right? As it gets bigger and bigger, this is in the denominator, so it is going to reduce my learning rate. Now, the exact reverse happens for parameters which has like few gradients. So for example, let's say I have a gradient, a parameter I, which has very small gradients. So this is going to be a very small number in the denominator, which means it is going to increase the learning rate. Is that clear? So when you have sparse gradients, learning rate is going to be high. When you have frequent gradients, learning rate is going to be low. Now the big advantage here is each parameter gets its own learning rate. Now, but the hyperparameter is still only one, right? Like there's only one eta. Imagine you have 100 parameters and you get 100 learning rates to tune. It's not possible, right? Like so with a neural network which has million parameters, like so definitely you cannot have million hyperparameters. Like so that the advantage here is like there's only one hyperparameter eta, but that eta is actually scaled by the gradient statistics that we are collecting over time. Is that clear? Now, do you see any issues with this equation? Any potential issues if you use this idea of integrating the gradients in the denominator? Yeah. Yeah.
Well, there are a lot of features. The values.
Sorry, what the values?
The values they will stay the same.
Why?
Because, the answer will always have a corresponding value.
Okay. There is one potential issue, right? Like so, like remember, like we start with random initialization, right? So initially you're going to get large gradients. So when you have a large gradient, that stays in the denominator. So what could happen is you have a large denominator, so you're going to have a very small learning rate. Now, even if you don't get large gradient, even let's say you're getting a medium-sized gradient, but if you do lots of epochs, you are integrating the gradient, right? So it is going to accumulate over time, and after maybe 10 to 20 epochs, it is almost equivalent to not learning anything, because your learning rate is going to be 0.000001. Like it is as if you're not taking a step. Okay, so this algorithm might saturate at some point, and like it is going to reduce and sometimes even stop the training. Now, how do I fix this issue? Anybody who has not answered? Yeah.
A window of like past epochs.
Okay, so you can consider a window of past gradients instead of considering all the previous gradients, right? Like, so in some sense, you want to forget some of the old gradients, like, so that, like, imagine you have a moving window of just the previous 100 gradients. Okay, now a naive way to do that is like just to implement a window which is basically keeping always the past 100 gradients. Now that is inefficient thing to do, in the sense, imagine you have a million parameters. If you want to store the past 100 gradients, it is 100 million values, right? Sometimes you can't afford to store 100 million values, like, or let's say you have a billion parameter network, right? Like, so then you cannot do that. So a smarter way of doing the same windowing idea is like to have a running average, or like a moving window, like, so, which is a soft window. Okay, so this is what we are going to do. So this improvement over undergrad is called RMS prop. Okay, so the idea of RMS prop is I'm going to maintain G squares. Okay, this expected value of G squared is going to be some rho times the past value plus 1 minus rho times the new gradient square. Okay, now the root mean square of G is defined as square root of E of G square plus epsilon. Okay, and theta t plus 1 is equal to theta t minus eta divided by RMS of G times GT. Is that clear? So the main difference between RMS prop and undergrad is the denominator. So in the case of undergrad, the denominator is square root of sum of squares, right? Like of all the previous gradients. Now this is also square root of sum of squares, but this sum of squares is a moving average, like moving thing, right? Like, so it's rho times the past value plus 1 minus rho times the new value. Now depending on what is the value of rho, you're going to forget the past sooner, like, or later. Okay, so rho here. Okay, so this is called decay constant. It tells how quick the past memory decays, and this is also usually set to 0.9. But this is just a default value, but you have to tune this, of course, like if you're using RMS prop. Is that clear? Now, one trend that you can see already here is like, along with alpha or eta, the learning rate, all these modern optimization methods also introduce more hyperparameters, which means you have to do a little bit more tuning to get things work. Is that clear? Any questions so far? Okay. So now we are going to look at another algorithm, okay, so which is called Ada delta. Now, so to motivate this algorithm, like, let's go back to SGD. Okay, now consider SGD. Your theta t plus 1 is equal to theta t plus eta times GT. right? Now, another way to put this is theta t plus 1 is equal to theta t plus some gradient. Okay. Now, this is a simple exercise that you would have done in your high school physics, right? Like, so when you have an equation, all the units of the term should match. You cannot have one term which is in centimeter and another term in meter, right? Like, so like every term in the equation should have same unit. Now let us look at this gradient descent update rule and consider like the unit of each terms involved. Okay. Now let us say that the parameters have some hypothetical unit. Okay. So then what would be the theta has some hypothetical unit. Okay. Now what would be the unit for the gradient? So the unit of the gradient, okay, the del theta t is basically proportional to unit of gt, because eta is a scalar, right? So the unit of del theta t is proportional to unit of gt. Now what is gt? So it is actually proportional to dou j by dou theta t. Okay. Now if we assume that the cost function is unitless, then this is basically 1 over unit of theta t. Okay. So you see some mismatch here, right? So you have a particular unit for the left hand side. In the right hand side, you have two terms. One has that hypothetical unit, the other one has 1 over that unit. Okay. Now this is true not just for SGD but also for SGD with momentum or SGD with Nestro's accelerator gradient. Okay. Now what about undergrad and RMS prop? So can we check RMS prop, for example? In the case of RMS prop, so this is 1 unit. This is also 1 unit, right? Now here you have 1 by unit, and you also have the root mean square of the gradient, which is also another 1 by unit, right? So these two things cancel each other. So this whole update is unitless. Okay, so both RMS prop and undergrad actually are unitless. Is that clear? So with this kind of motivation, right? Like, so now let's also revisit our Newton's method, or the Newton-Raphson method that we have discussed like a while back, right? So like if you remember Newton-Raphson, it is a second order optimization method, which was also using the curvature information, right? So the gradient update in Newton-Raphson was proportional to H inverse of G. That's right. So which is actually proportional to dou J by dou theta T divided by dou square J by dou theta T square. Okay. Now you see 1 over unit divided by 1 over unit square. So this is actually proportional to unit of theta T. Okay. So in some sense, Newton-Raphson is doing the right update for my parameter, because the thing that I'm adding to the parameter is in the same unit as my parameter, while all the other algorithms like SGD, SGDM, RMS prop, and so on, like, so they are not doing the right update, going by this like intuition, right? Now this means that can we come up with an algorithm which is similar to Newton-Raphson, but not as computationally like costly as Newton-Raphson? So now if you remember, the biggest bottleneck in Newton-Raphson is this H inverse, right? Like, so this Hessian matrix is a huge matrix, and every time you have to take the inverse of this matrix, like, which is an order n cube operation. So you can do Newton-Raphson for simple models, but for complex models and for big neural networks, you cannot do Newton-Raphson efficiently. Okay, so how do I come up with something which has same unit like Newton-Raphson. Okay, so to do that, like we are going, that is what ada delta is going to do. So to do that, like we're going to take this equation and do a little bit of rearrangement. Okay, so now del theta t is equal to dou j by dou theta t divided by dou square j by dou theta t square. Right? I'm just going to do a little bit of rearrangement here, like move things around. So this is going to be 1 over dou square j by dou theta t square is equal to del theta t by dou j by dou theta t. Is that clear? I have just jumbled the fractions. Okay, now you can see that in RMS prop, we have a root mean square of this entity already, right? Ada delta is just a small change to RMS prop. So what we are going to do is we are going to also add the root mean square of this entity. Is that clear? So my ada delta equation is going to look something like this. So del theta t is equal to minus RMS of del theta t minus 1 divided by RMS of gt, okay, multiplied by gt. So in the case of ada delta, we don't have the learning rate alpha, but I think you can add a learning rate here, like it doesn't matter. But the update equation is a bit different from RMS prop in the sense, in the numerator, you have another RMS equation. Like this time it is an RMS over the updates. Is that clear? So any question? This is ada delta. Okay, so now we have seen things like ada grad or RMS prop or ada delta, right? Like so, like out of these three, the most common thing that people use is RMS prop. Okay, so RMS prop is like a default adaptive optimization method. Now we also discussed about momentum, right? Now in theory, like we should be able to combine all these adaptive gradient methods with momentum-based methods because they are just orthogonal to each other, right? Like so, I can combine ada grad with momentum, like or ada delta with momentum, RMS prop with momentum. Okay, now so that combination is kind of the current state of the art. Okay, so most often when you see people using, especially trying to optimize deep neural networks, like so the default optimizer people use is called ADAM. Okay, so which stands for adaptive moment estimation. Okay, now ADAM is nothing but a kind of RMS prop with momentum. Okay, so it's a combination of adaptive gradient and momentum based methods. So how do we do that? So we are going to maintain two vectors. Okay, the first vector is the estimate of the first order moment. So mt is going to be beta 1 times mt minus 1 plus 1 minus beta times gt. We are also going to have the estimate of the second order moment. Okay, so vt is going to be beta 2 times vt minus 1 plus 1 minus beta 2 times gt square. Okay, now if you think about it, this corresponds to the momentum, right? Momentum method, and this vt term corresponds to the RMS prop equation, like the denominator thing. Okay, so I'm going to put these two things together, okay, and write an equation which is going to be theta t plus 1 is equal to theta t minus eta times mt by vt. Is that clear? It's a very simple algorithm. Like so, you have a running average of gradients in the top, and another running average of the gradient square in the denominator. Okay. So, however, there is a small issue here. The issue is like initially, like typically, you will initialize your MT and VT with 0 vectors. So it will take some time to get out of the 0. Okay. To avoid that, like we're going to do some bias correction. So since they are biased towards 0, we're going to do some bias correction. Okay. So we are going to compute m hat, which is basically mt divided by 1 minus beta 1 power t, and v hat, which is vt divided by 1 minus beta 2 power t. The t is the time step. So as the time step, when the time step is small, this bias is going to be mitigated and it is going to disappear as time increases. Okay, so here I will use this m hat and v hat instead of m and v. Is that clear? Any question? Okay, so what we have done in today's lecture is like we took all these algorithms that we have learned so far, and now we can accelerate all these algorithms and speed up our training process by just switching from SGD to Adam. Okay, so like for example, like you can go back and do your linear regression, like but with Adam instead of SGD, or SGDM instead of SGD, and see like the difference between like the convergence. Okay, and of course you can use these adaptive gradient methods for your Kaggle competition as well. So it is going to help you in learning faster. And for most of the recent neural network architectures, it is important that you use some fancy optimizer, because plain SGD will have a lot of issues. Is that clear? Now, before we move on, like I want to give a bunch of general tips on optimization. Okay, first of all, Adam is the most default optimizer that you would see in every single paper that you are reading. Okay, so the crazy thing is it's not a very old optimizer. I think Adam was introduced in 2015 or 16, but it has become like the default optimizer that everybody tries. But my general advice is don't take Adam for granted. Okay, there are a lot of problems where it is possible to get better performance with just good old SGD with momentum. Okay, there is no clear winner, even though like it looks like Adam is the clear winner. Okay, like this comes from no free lunch, right? Like so, like you cannot come up with a universal optimizer which can be good for all the problems. It is simply not possible. Okay, so different problems would require different optimizers, and this is one of the most crucial hyperparameters that you should tune in your application. Like so when you're working on a problem, let's say that is the problem that you care most about, like a 1-year project or 2-year project, don't just do Adam. Like so you should start with a hyperparameter search over different optimizers and see which optimizer is suitable for your problem, and then start exploring more. Okay, the first tip is like don't use Adam as a default optimizer. It's a common mistake that even established researchers do. Like so, like don't do that. And there are a few other usual strategies. Like so, for example, okay, first of all, try all or more optimizers than just Adam. Okay. It is always a good idea to shuffle your data before every epoch, especially if you're using stochastic gradient descent or mini batch gradient descent. You are going through your data in an order, right? So if that order was a bad order, then your optimization is stuck with the bad order. So that is why every time you start a new epoch, you should shuffle your data set and then go through this shuffle data set. Okay, and in general, it's a good idea to use batch norm. Like whenever things are not working, probably add a batch norm there. Like so, it could help you in improving your like learning. And you should always use early stopping. Okay, so which means you wait for some epochs. If your validation performance doesn't improve, you can stop there. Okay, so instead of blindly running 1,000 epochs, you could just stop at 150th epoch if you see that there is no hope for like learning further. Okay, and sometimes adding noise to your gradient helps. Okay, there is a lot of work showing that if you add a little bit of noise to the gradient, it might be helpful. But remember that there is already some noise coming from stochastic gradient descent, and there is also some noise that comes from, like, for example, quantized training methods. Like, so for example, if you want to train your algorithms faster in GPUs, instead of using 32-bit operations, you can use 16-bit, or I think nowadays even 8-bit is possible with PyTorch and other frameworks. So the advantage is, like, you take less memory and you're computing things faster. The added advantage is it introduces some noise, which could be helpful. Is that clear? Any questions? Okay, so okay, I can either start now or take a break and have a slightly longer third session. So which one do you prefer? Because we're going to switch topic. So if I start now, probably I'm going to break in 10 minutes. So let us just take a break now, and we will continue at 2:35. Okay, so that gives me more time for the next topic. So we will stop here and take a break.